Okay, so let's get started. So last time we talked about conditional probability, right? So in this probability space, we have omega outcome space and the sigma algebra defined on events and the probability law. And then for any two events, E and A, suppose these are two events in the sigma algebra, then we can define conditional probability as the following. So let's say we are considering A conditioning on the event E. And then by definition, we define this as the joint event, the probability of the joint event over the probability of the event E. Okay. Well, the joint event is basically the event that is the intersection between the event A and event E, because these two events, by definition, are subsets of the omega, big omega. So we can take their intersection. So for this notation, we still denote this conditional probability as a kind of probability, because we write probability of A conditioning on E. So this this motivates us to consider the following question: is this a valid probability measure? So consider this one. Is this a proper probability measure? Right, because we still call this probability. It's a conditional probability. But when you call it probability, you need to make sure that it is a valid probability measure defined over this probability space. Right? And this is different from this probability measure, because this one is the original measure associated with this probability space. Now, based on this probability measure, we are further conditioning on any event E, any of the event E. Now the question is this conditional one a proper probability measure? Okay. And in fact, so to check this, we just need to check the three axioms for probability measures. So the axiom one is to show that this probability measure assigns probabilities between 0 and 1. Okay. So this event E is fixed, and then this probability measure can be applied to any event on this sigma algebra. Right. So this is the first requirement. Well, this is the first axiom of the probability measure. So we can check this one. So for any event A, we just need to check this conditional probability. And by definition, is the joint event over probability of E. Okay. And we know that these two probabilities, this is the probability of this joint event, and this is the probability of this event. They are both defined on the sigma algebra, and these two probability measures are the original probability measure. So by definition, both the denominator and numerator, both of them are non-negative. And of course, here I should add an additional condition that PE is not 0. Okay. So the denominator is guaranteed to be positive, actually, positive. Right. So because there are probabilities, so there must be both of them must be positive. So the ratio is positive. Right? So it's non-negative. It's non-negative. So this conditional probability for any applied to any event A is guaranteed to be non-negative. Okay. So this is just one side. Now the other side, we need to check that this probability is less than 1. So can you say something about this ratio? How to show that? Can we show that it is less than 1 from this definition? So the denominator is the probability of this joint event, and the numerator is the probability of joint event. The denominator is the probability of event E. So which one is bigger and which one is smaller? Any ideas? So what is the justification for that? Right, because the top is the intersection, which must be included in event E. So by one of the properties of probability measures, we know that the numerator is smaller, less than equal to the denominator, because this is a subset of the event E. Okay. So therefore, this one is less than 1. Less than 1. So this conditional probability is less than 1 and bigger than 0 for any event A. Therefore, this conditional probability measure satisfies the first axiom. Okay. So this is first one. Now for the second axiom, we need to check that this conditional probability applied to the entire omega space. This is the biggest event, okay, in this probability space. Now the probability of this one must be 1. And by definition, this is the probability of the joint event divided by probability of E. But then this omega is the entire outcome space. So taking intersection with any subset, we know that this is the event E itself. Okay, because omega is the biggest event and E has to be inside omega. So when you take intersection, it is just event E. Right? And this is 1. And this shows that indeed, for this conditional probability measure, we still have the conditional probability of this omega is 1. So the last axiom is the most important one. So it says that if we have a sequence of disjoint events, Then we need to check that the conditional probability so this conditional probability measure applied to the union event is equals to the summation of the conditional probability of each event. All right, so this is the last axiom. So that for disjoint events, we can calculate their probability measures separately. Okay, to show this, again, we follow the definition of this conditional probability. And by definition, it is the intersection divided by the probability of event E. And then we need to think about this event, which is the intersection between event E and this union event. Well, this AI, they are disjoint from each other. So if you think about that, here are some disjoint sets. Okay. And the union of this AIs is basically this the union of these areas, but they are disjoint. But now you are taking so first of all, we union all these events, which gives us all these different areas. And then the entire all these different areas will take intersection with another event E. Well, this E could be any event. So for example, it could be this one. Once you do that, we can see that these are the intersection parts. Okay. So these are the intersection parts. So intuitively, this equals to I first take intersection between each AI and event E, and then I union all the intersection parts. Okay. So this equals to probability of, I first take intersection between each AI and E, and then I union all the intersection parts. Okay. In fact, this is one of the basic properties of the set theory. Okay. So we can do the intersection first and then take the union. But then think about this form. Now this is a union of a bunch of events. Right? So each event is AI intersect with E. And then we take the union of all these events. Now, because each AI, they are disjoint. Right? So the AIs are disjoint. Therefore, after we take intersection with event E, these intersection parts, they are also disjoint with each other. Because the intersection part must be within this each AI, and all these AIs, they are disjoint. So therefore, these are disjoint events. Okay, for different I, because those AIs are disjoint. So then we have inside we have a union over a bunch of disjoint events, and then we are looking at their probability measure. Right? This is the original probability measure. We don't have conditioning here. Right? So therefore, we can apply because this P is a valid probability measure. So we can apply the axioms of probability measures, the third axiom of the probability measure to this one, and claim that this equals to sum over the probabilities of each individual event. Right. So this is by the axioms of this original probability measure. And then we still need to divide by probability of E. Okay. And now you can see that this ratio, by definition, we call it the conditional probability. Right. This is just definition. So therefore, in the end, we conclude that this equals to the summation over all the conditional probabilities. Right, so from the left-hand side, you can compare the left-hand side with right-hand side. You see that this is exactly the form of the third axiom. Okay, so the only difference is that now we are conditioning on a fixed event E. But other than that, when you apply to a union of disjoint events, we can compute this conditional probability by accumulating the conditional probabilities of each event, each individual event. So therefore, if you consider all these three axioms, they all hold for this conditional probability, So this is a proper probability measure. Okay. So the conclusion is that this is a proper probability measure on the probability space. So that's why we can define this conditional probability and talk about conditional probabilities in real life, right? Because it turns out that this is a valid probability measure on the probability space. Okay, so let's consider example. So let's say a couple has 2 children. And the probability of having a boy and a girl is equally likely. Okay. So for part A, we want to look at the probability that both of the child are boys given that the younger is a boy. Right, so these are two events. They belongs to the same probability space, because we're always talking about these two events are all about these two children. Right, this event says that both of them should be boy, and this one says that the younger one is a boy. Okay, well, the older one could be either a boy or a girl. So these are two events from this two proper events for this random experiment. Okay. So I think I can give you 2 minutes to think about this problem. Okay. You may start with what are all the possible outcomes, and then think about these two events. Okay. Once you list all the possible outcomes, how can you represent these two events? And then follow the definition of conditional probability. Okay. So any thoughts on the probability on the outcome space? So how would you define the outcome space? Right. So here we have two children, right? So we're talking about their gender. So here I can always, for each outcome, basically is either so we're talking about gender of these two children. So I can write them in a vector of 2. Well, for this one, I can always denote the younger child, and for the second one, I will denote it as the older one. Assume that one is always younger and one is always older. So both of these two positions can be either a girl or a boy, right? So in total, we have 2 to the power of 2. We have 4 different outcomes. So omega is could be two girls, could be, right? So this one means the younger is a girl, while the older is a boy, and the younger is a boy, and the older one is a girl, and we could have two boys. Right. So in total, we have 4 different outcomes. And because each child is equally likely to be a boy and a girl, so every outcome has probability 1/4. Okay. So these are the basic setup for the outcome space. And because it's a finite outcome space, so we can always consider the sigma algebra as the power set. And then we can talk about this probability, this conditional probability. Okay. So this conditional probability, now once we have this notation, we can translate these sentences into these outcomes. So this is event E1. This is event E2. Now, event E1 corresponds to the case where both are boys. So that means this outcome, single outcome. And that's the only case where both of the children are boy. Event E2 is the event where the younger is a boy. So we look for the younger, the first position. The younger is a boy. We have this one and this one. But these two, the younger is a boy. So we have event E2 is the set of these two outcomes. Okay. So this is E1, this is E2. Okay. They are different events. And then we can follow the conditional probability rule to calculate conditional probability. Well, in the numerator, we need to look at the probability of the joint event. The joint event is the intersection of these two events. And then you see that the intersection of these two sets is only this event, this outcome. Okay, so this is the intersection of these two events. And then the denominator is the probability of this conditional event. Okay. And now we can calculate the probability, because we know that every outcome happens equally likely with probability 1/4. So the numerator is 1/4. For the denominator, these two, right? These two outcomes, this event has two outcomes, and they are disjoint from each other because they are disjoint in this outcome space. There are two different outcomes. So according to the probability measure, the axiom of probability measure, this probability equals to the sum, equals the sum of these two, the probabilities of two individual events. So it's 1/4 plus 1/4. Right. Okay, to be more specific, this is the union of these two outcomes. So I should write union. Sometimes I write a comma, means that it is the set. This set contains these two elements. Okay. You can also understand it as a union. So basically, this event has two different It's a union of two different outcomes. Okay, so here's also can be also understood as union. So we are looking at the probability of a union of two disjoint outcomes. So by the probability rule, we need to add up their individual probabilities. So in this case, both of them are 1/4. So this gives 1/2. So this is the probability of this conditional event. And let's look at another question. It's the probability that both are boys given at least one is a boy. Okay. If you already know one of them is a boy, what is the probability that both of them are boys? Well, intuitively, you may say it is 1/2, because if you know one of them is boy, then the other one could be a boy or a girl. And then intuitively, if the other one, the probability of the other one being a boy is 1/2. So that might be the conclusion. But if you follow the probability rules, conditional probability rules, you will end up with a different conclusion. So let's look at these two events. Both are boys means that according to the outcome that we listed above, this is the only case where both of them are boys. And given that at least one is a boy, so let's look at all these outcomes. We have 3 different outcomes that has at least one boy. Okay, so these are all the possible outcomes. Right, so this event has 3 outcomes. And then we calculate this conditional probability. Well, the numerator is the probability of this joint event. And if you look at the intersection between these two, we only have this one. And this is the only common outcome. So that's the intersection. Well, the denominator is the probability of this conditional event. Okay, and because this one we know is 1/4, and the denominator, each outcome happens with 1/4. We have 3 disjoint outcomes, so it's 1/4 plus 1/4 plus 1/4, which gives actually a different answer, 1/3. It's not 1/2. Yeah. So basically, when we calculate conditional probabilities, you need to understand what are these these 2 events. This is the event of interest. This is the conditional event. What are these 2 events corresponds to in the outcome space? Okay. Once you figure out their corresponding representation in the outcome space, you just need to take the intersection between these 2 events and calculate the conditional probability based on the definition. Okay. So this is all about conditional probability. It's a very, very simple definition and generalization of the original probability measure. And this is exactly how we describe conditional events in daily life. Whenever we say something happens, given some other things happens, we are really talking about conditional probability. And this is the rigorous framework to define everything. Okay, this is conditional probability, and next one, which is a very important, also very important concept called independence. And we have seen this in the introductory level probability courses. So here we are talking about independence of two events, multiple events. So the definition is as follows. So two events, E1 and E2, are independent if the probability of the joint event equals to the product of their individual probabilities. So this is the definition. So basically, if we consider two independent events, then you can calculate the probability of the joint event by taking the product of their individual events. So this is intuitively, this means that when you calculate their joint, the probability of their joint event, you can just start from any one of them, calculate the probability, and then multiply the probability of the second one, as if they are independent from each other. Right, so this is just a definition. We call these independent if this equality holds, and on both sides they are well defined. We know that these two are events from the sigma algebra. Okay, so we can look at their probabilities. We know their joint event is also in the sigma algebra. We can look at their probability measure. So this is just a definition. But this definition has many interesting implications. So when we intuitively, when we talk about independence, maybe we would imagine that these two events has nothing to do with each other, right? So that's the intuition from our daily life. But really, we never rigorously defined we never rigorously defined this. The sentence has nothing to do with, right? This is not a rigorous sentence. Here we need to have a quantitative way to define and measure this independence between these two events. And a somewhat counterintuitive implication is that independent events defined in this way, right, may not be disjoint. They may have some overlap and still be independent. And we will see that in a moment. The first thing is that independent events are usually not disjoint. if they are always disjoint, then why not just define independence as disjoint events, right? So there must be difference. There must be a difference between independence and disjoint. If E1, in fact, if these two events are disjoint, then we know that they are joint event, right? Because they are disjoint, so their joint event is empty event, which is zero probability, which has zero probability. Therefore, if this happens, and in order for these two to be independent, in order for this equation to hold, right, this is the definition of independence. If these two events are disjoint and also independent, then we must have the right-hand side, this product equals to zero. Which means either this one equals to zero or this one equals to zero. So basically that basically means that either of these two events has to be a null event. And this is trivial. Right? This is trivial because we are not talking about null event in practice. So disjoint and the independence, they are not exactly the same. This is a trivial case. We would like to talk about some normal events that are independent. Okay, and apparently disjoint events is different from independent events. Later on, we have some examples to illustrate this. So the right way to intuitively understand independence . So the right intuition is to consider the conditional probability. So let's say two events are independent, so that by definition, they satisfy this equality. And then we look at their conditional, this conditional probability. Okay? And by definition of conditional probability, this is the joint event divided by the conditional event, probability of conditional event. And because they are independent, the probability of the joint event equals to the product of these two. And then we cancel this term, so we get probability of E1. Okay. So this shows that for independent events, if E1 and E2 are independent, then the probability of E1 given E2 equals to the probability of E1 itself. So intuitively, this means that doesn't matter if you condition on E2 or not, because they are independent, right? They have nothing to do with each other, in the sense that this conditional probability equals to the original probability. So you don't really need to care about this conditioning. And similarly, you can show that E2 condition on E1 is just probability of E2. Okay, so this is the right intuition, right way to intuitively understand the definition of independence. Okay, so any questions about independence? Okay, it's not working again. Let me refresh this page. Okay, works now. Let's consider one example. On independence. So consider a rectangle. It has two sides, S1, S2. And let's pick these two sides. From this set. Okay. Independently, and uniformly at random. Okay. So independent means that, well, we just talked about the definition of independence, right? And uniformly at random means that every S1 and S2, they are picked from these three numbers uniformly with probability 1 over 3. So we know that from this uniformly at random, we know that S1 can take values of 1, 2, and 4 equally likely. So they have equal probability, and similarly for S2. Okay, similarly for S2. Now the question is, what is the probability that the area of this rectangle is bigger than 15? So each S1, S2 have 3 possible outcomes, right? So in total, we have the outcome space has 3 by 3, which is 9 total outcomes. And among these 9 total outcomes, we need to make sure the area is bigger than 15. Actually, if you look at these 3 numbers, seems the only case is when S1 and S2, both of them take values of 4. Right? 4 by 4 is 16, which is bigger than 15. All the other combinations are smaller than 15. So this event is exactly means S1 equals to 4 and S2 equals to 4, right? So we translate this event into the language of S1 and S2. Okay, now the event is much more clear. So we just need to look at the probability of S1 equals to 4 and S2 equals to 4. but these two are generated independently and uniformly at random. Okay, and by independence, exactly by the definition of independence, we can say that by independence, because they are generated independently, so this joint probability, the probability of this joint event equals to the product of the probability of these two events. Because this event means S1 equals to 4, and so here this should be understood as intersection, right? These two must happen simultaneously. So S1 equals to 4, and at the same time, S2 equals to 4. And then by independence, we can calculate the product of their individual probabilities. And then for each individual probability, we know that they are picked from these three numbers uniformly at random. So each one is 1/3. And that gives 1/9. Right. So whenever you apply independence, you want to leverage the property of independence, you need to follow the definition, right? So it's the probability of the joint event. Right? Well, we are always looking at the joint event. This probability can be decomposed into the product of these two smaller probabilities. Yeah. So I think we will have some problems in homework 2. Yeah, we will have some problems regarding on the independence. Okay, so what is a example? Well, two independent events are not disjoint. You can think about this. Let's say we pick numbers from 1, 2, 3, 4 equally likely. And E1 corresponds to the event where we pick 1 and 2, where E2 corresponds to the event that we pick 2 and 4. And apparently, E1 happens with probability 1/2 because we have this event has 2 outcomes. In total, we have 4 outcomes. Each outcome happens equally likely. So it's 2/4, 1/2. And the same holds for E2. Right. And probability of E1 intersect E2, this joint event is the probability of picking 2. Right, the intersection is only 2, the number 2. The probability of picking 2 is 1/4. So these two events are independent by the definition of independence, right? The product of these two equals to the probability of a joint event. But here you can see that these two events are not disjoint. So disjoint and independence are completely different concepts. And this is all about independence. It is also very basic definition, but it's a little bit tricky to understand it. So the right way to understand independence is through this. To intuitively understand independence is through this conditional probability. Right? Independence means that when we consider one event conditioning on another event, we can just ignore the other. We can just ignore this conditioning and consider the event only. So in this sense, so when we say E1 has nothing to do with E2, we really mean this conditional independence. So this means E1, when conditioned on E2, actually has nothing to do with the event E2. So they are independent intuitively. And then let's consider a very useful technique called total probability lemma. This is very useful when for many problems, we will have to decompose the event of interest into a bunch of smaller events. And before when we introduced the monotone events, right, that is one way to decompose the big events. But here is another way. So let's consider a sequence of events that forms a partition of the outcome space. So partition means, recall the definition of partition. It means that all these events are mutually exclusive. And their union gives the set omega, right? So it's like you have to cut this omega into small pieces, where each piece is disjoint from other pieces, and their union covers the entire omega. So this is a partition. There should be non-overlapping, right? So it's mutually exclusive. So if we have a partition of this omega space, and also suppose each partition has positive probability, okay, to avoid some numerical divergence issue. Then for any event A, we have this partition lemma. So the probability of A is sum of all the partitions and we consider the probability of EI times probability of A given EI. So this tells us that whenever we have a partition, we can calculate the probability of any event by simply considering the probability of each partition event multiplied by this conditional, the probability of this conditional event. Now this, we will see many problems later. This is very useful when sometimes understanding event A may be very hard. This event can be a very complex event. But sometimes the problem naturally has a very simple partition. So we can, well, the probability of each partition is very easy to calculate. And also, this conditional probability is also relatively easy to compute in that case. So therefore, we can just decompose the probability of this event of interest into such a form. And actually, the proof of this lemma is very straightforward. We just basically need to show that the event A on the left-hand side can be represented by all these events on the right-hand side in a certain way. So from this figure, if I draw any event, let's suppose this is event A, then I can, because all these EIs, they form a partition. So certainly I can naturally decompose this event A into these subsets. Well, each subset is the event A intersect with one of these partition events. So to make this formal, again, we are using the basic tools from set theory. So A equals to A intersect omega. And this is a trivial statement because event A has to be inside all the possible outcomes. And we know omega is covered by the union of all the event EI. Right? Because EI forms a partition, so omega is exactly equals to the union of all these partition events. And then we apply the basic property of set theory. So we have this rule. So you can switch the order of the intersection and the union. Right, from this figure, you can see that A intersects with, this is the union of these events, it's a big omega set, equals to, I can first intersect A with each of these partition events, and then take union of all these intersections. They are the same. And now, because all the EIs are disjoint, so this set all these intersection events, they are disjoint events for different I. And because they are disjoint, so we can conclude that, so first of all, this A equals to this event, so the probability measure, their probability measure are the same. But then these are union of disjoint events, so we can apply the axiom of the probability measure. So this is sum over I of the probability of this joint event. And this is the probability of a joint event by the conditional probability. By definition of conditional probability, we can decompose it as PEI multiplied by PA given EI. Right, so this proves this partition lemma. So it's basically from this diagram, we are basically partitioning the probability mass of the event A over the entire the partitioned events over the entire omega space. Right, so this is proved by leveraging the basic tools from set theory. So we can consider example consider two boxes. Box one has two green balls and 3 red balls. And box two has 4 red balls and 3 green balls. Okay, 2 boxes. Now here's the problem. We pick a random ball again, we consider simple case uniformly at random. Okay, so every ball can be picked with the same probability. We randomly pick a ball from box one and put it in box two. Okay, you pick one ball from box one, put it in box two. And then pick a random ball from box two. Okay. Pick one ball from box one, place it into box two, and then so box two will have 7 + 1, 8 balls. And then you pick one ball from box two uniformly at random. So what is the probability that the second selected ball is a green ball? But the second selected ball means is the ball where you finally picked from box two after you place one ball from box one to box two. So apparently, when you look at the second pick, it really depends on it is affected by your first action. Right? In the first action, you pick a ball from box one, place it in box two. Well, this pick could be green, either green or red, and that will certainly affect the probability of of your second peak. So therefore, here we need to consider a partitioning, because we know that the second peak is determined, is affected by your first peak. Your first peak has two different cases, right? You may either pick a green ball or red ball, and this forms a partitioning, and this naturally forms a partitioning over all the outcomes. So we can define E1 as the event where the first peak the first selection from box 1 is a green ball. And then its complement is the other case where you pick a red ball. Okay, so these two are complementary cases, and they form a partition. And then, so these two form a partition, and then we consider event A. We define this as the event A. So this is the event of interest. Right, the second selection from box 2 is a green ball. Now we can leverage the partition lemma to look at probability of event A. Now we can, by the partition lemma, this equals to, you go back to the partition lemma, this equals to sum over all the partitions, well, the probability of each partition multiplied by this conditional event, right? So here we have two partitions. So it's the first, so the first term is the probability of E1, the first partition multiplied by a given E1, and plus the second term is E1 complement. Right, and then we look at all these individual probabilities. Let's see if we can calculate them. So probability of E1 is the event that your first selection is green. Well, your first selection is from box 1, so you clearly is 2/5, right? The probability is 2/5. Okay. Now, what is probability of A given E1? Well, A given E1 means that, think about that, we are given that E1 happens. So you in your first selection, you select the green ball. And then this green ball is placed into box 2, right? So then you will have 4 green balls and 4 red balls in box 2. So given this event E1, what is the probability that you pick a green ball from box 2? Given that happens, box 2 will have 4 green and 4 red. So the probability that you pick green is 4/8. It's 1/2. Right. So this turns out to be very easy to calculate. And then you look at the other case. E1 complement has probability, well, 3/5. And then E1 complement means that the first time you select a red ball, okay, you select a red ball and then you place it in box 2. So box 2 will have 3 green and 5 red. And conditioned on this event, the probability that you pick a green is 3/8. Okay, so and then you just sum them up. Right. So in many cases, I think you will see that in the homework problems, finding a proper partition will make it more convenient to analyze the probability of some events. Especially, some in this case, your second action depends on your first action. So really, your partition has to be over your first action. You need to consider different scenarios in the first action, and based on that, conditioned on that, right? So we first consider different scenarios in the first action, and conditioned on different scenarios of the first action, then it is easy to understand your second action. So these conditional probability are relatively straightforward to calculate. Okay, so I think I will stop here. So you should be able to complete homework 2. And on Thursday, we will probably finish lecture 5. And yeah, you may also work on homework 3. It's part of homework 3. So I will see you in the office hour this afternoon. Okay, see you guys. Oh, this is Thursday, so next Tuesday we will probably finish lecture 5.